So in the last class, we started with fourth module. So we started discussing about uh, changing the user IDs, different user IDs, real user IDs, or we can also change group IDs and all, effective user IDs, how to change. Then what do you mean by interpreter file? Okay. What is the format of the interpreter file? And then we started discussing about the system function, okay, which is used for executing any command in either C or C++ language. Okay. So today we'll discuss about process accounting. In the Unix system, it provides an option to do process accounting. So process accounting is nothing but it is getting the information about the process. Okay, so information includes getting the real user ID, real group ID, uh, any controlling terminal information, how much CPU time it has been used, okay, how much memory it has been process has used, what are the different types of flag it has been used. So all this information can be accounted in a uh, uh, in in information that we call it as process accounting. Okay, so when enabled, the kernel writes, okay, the kernel will writes an accounting record each time a process terminates. So this is important. Okay, so process accounting will have the information about the process, not when it will start, but when it each time the process terminates. Okay, so we are not we are not related, we are not interested with when the process starts. Okay, so it will have the information only when the process terminates. Okay, so as I already said, the typical record, okay, which will be of typically of 32 bytes of binary data. Okay, this record is of how much? 32 bytes of binary data. Okay, and with the name of the command, the accounting records are typically a small amount of binary data with the name of the command. Okay, comma, it will have the amount of CPU time used, user IDs, group IDs, starting time, and few more informations. Okay, next, to know the process informations, okay, we need super user privilege. Okay, so only if you have super user privilege, only then you can get the information about the process. Okay. Now, a person with a super user privilege can use this command. So this is a command. Okay, ACC account turn. Okay, so this is the name of the command that is used for getting the process information. So this command with the path name argument to enable the accounting. So you can give, okay, you have to use this command ACC turn, okay, and you have to write the path name. So in this path, okay, the accounting information will be stored. So accounting records are returned to the specified file, which is usually, okay, so this is usually the path you will specify here. Okay. So in this path, a particular file, a specified file will be having the accounting records of the process. Okay. Accounting is turned off by executing act on without any arguments. So when it is done, so when you write act on with the path, okay, so the kernel will start writing the accounting record of a particular process to the specified file, and after some time you have to write the same command again, okay, to off the writing process, okay, to terminate the process information. Okay, so this is to start to get the information, and this is to off the execution. Okay. So data required for accounting records such as CPU time, number of characters transferred is kept in the kernel process table. Okay. Now we said that we are getting the information about the process like CPU time, user IDs, group IDs. Now the question is where this information will be stored. Okay. So for that, The answer is the kernel will store that information where in the process table. So when you execute this command, action command with the path name, the kernel will make use of this process table to get all the information about the terminated process. Okay, and initialize whenever a new process is created. Okay, so this table is initialized whenever the new process is created as in the child. Okay, after a for command. Okay, so each accounting record is written when the process terminates. Okay, not when the process starts, when the process terminates. This means that the order of records in the accounting file. So here in the accounting file, okay, the order. Okay, usually when we are running a system, we will not be having just one process. We'll be having a different process, correct? And we need, if you want information about all, assume that 5 processes are there, we need those information about all the 5 processes. Okay, so it means that order of records in the accounting file corresponds to the termination order. That means assume that P1, P2, P3, P4 and P5, these are the 5 processes in the system. Okay, now in the file, so this is your accounting record file which is there in this particular path. Okay, now how the order will be stored? Okay, so it is not the order that it, like P1 will be, information will be there first, second P2, P3 and all. No, okay, assume that this will terminate first. Okay, this will terminate first. Then P2's information will be there first. Okay, then assume that this will terminate second. Okay, then in the file next P5 will be there. Okay, similarly if P1 terminates next, okay, then P1 information will be there next. Okay, so like this, okay, the file accounting record file will be having uh, the information that is corresponding to the termination order of the process. Okay, not the order in which they are started. Okay, it is not the order in which they are started. Then accounting records corresponding to the process, not a program. So here accounting record will not have any program information, it will be having only process information. Then a new record is initialized by the kernel for the child of the fork, not when a new process is executed. Okay. So for the child, we'll be having the all these record informations. So here we have a structure. Okay. So structure of the accounting record, it is defined in the header file. So this is the header file we need in the program. So this is the header file. This is slash a to acc.c.h, account.h. Okay, so this is the header file we need for, okay, executing the structure. So we need this type def. Okay, u short is defined as computer T. Okay, and this is a structure. So this structure can be used for accessing different information like what type of flag the process is using, what is the terminating status, real user ID, terminals, calendar time, CPU time, memory used, clock ticks, how many clock ticks or clock cycles, okay, how many bytes of data has been transferred. Then, so similar information you can get. Now here, so these are all straightforward informations. Okay, CPU time, then terminal name, user IDs, and all. They are single word. Okay. So what we have to understand structure member, that is account flag. So this is important. Okay, the flag. So values of account flag for from the accounting record. What are the values it can take? So these are the values you can specify for the first member account flag. Okay, so here we have different informations. You can go through this. Okay, so this will give you. Okay, this first one will give you a fork will give you the process is a result of fork but never called as ext. Okay, then this will give you all the information about this flag value will give you all the information of the process used by the super user, okay, with the root permission. Okay, then this flag value can be used by the process in the compatibility mode. Then next one, similarly, this will give you process dumped core information. Okay, then this is for getting the process was killed by the signal. Okay, information of all the process. Okay, using this flag you can get information about all the process that is killed by a signal. And the last one, this flag value can be used for getting expanded accounting entry, additional accounting informations about the process can be got using this last flag, A expand. Okay. So these are different flag values. We have a program here. So actually this program is a lengthy program and but very simple program. So I had written in 2 slides. Okay. So this is 2 slides. So here the program begins. Okay. Now we are having a main process, or we call it as a parent process. Okay. Now here, how many times we are using fork system call? So we know that fork system call is used for creating the child process, correct? So how many times we are using 1? Okay. Similarly here 2, and here 3, and here 4. So 4 times we are using the fork command. Okay, the fork function system call. So 4 times we are using. So how many childs will be created? 4 child process will be created. Okay, so I'll write C1, C2, C3, and C4. Okay, now this main process, that is parent process, will be given with the value greater than 0. Okay, child will be returned with the values 0. Okay. Now here PID not equal to 0. PID is not equal to 0 is what? It is not about child. We are talking about one which is having a value greater than 0. So parent will execute these 2 commands, sleep and exit command. Okay, exit functions. Okay, similarly here also second time. Okay, again the parent is executing sleep and abort function. Similarly, here also we are executing PID not equal to 0 is executing EXE, okay, EXE and exit 7. And the last one again, PID is not equal to 0, we are executing sleep 8 and exit function. Okay. And here, this diagram, complete diagram shows you the process structure for the accounting example. So previous one, how many childs we have created? This is your parent process. Okay, these are all. And how many childs we have created? 1, 2, 3, and 4. Okay. So similarly, what are the related functions we have? Okay, so shown you different functions. First one is sleep 2 and exit 2. Okay, sleep 2 and exit 2. Similarly, first child is having these. Child is having EXE. Third one is having sleep 8 and exit 0. Fourth one is having sleep 6 and kill functions. Okay. Now here, okay. So now here, this child, 4 child process and parent process may terminate in not in the same order, correct? First child, second child, or third child. may not terminate in the same order. So based on the task given, it may take its own order for terminating. Okay, now so we have to follow few steps here. The first one is to get the information about all these process, okay, accounting information about all this, how many we have, 4 child and 1 parent. We need super user privilege. So you have to become a super user, and which command you have to type? You have to type this command, okay, ACC T ON command, okay. And you have to specify the path in which you have to store the file. Okay, so become a super user and enable accounting with the ACCTON command. Okay, account on command. So this stands for account on. Okay, ACCT stands for account and on. So you are starting recording the information. Okay. So then what you can do is, once you have executed this command, you can start executing this. Okay, you can start executing this program. Okay, let me give this name as P1. Okay, P1.c. Let us assume that this is the name of the program. Okay, then what you have to do? You have to execute this program. Okay, dot a dot out. Okay, so that is program. What is the name of the program? P1 dot. You can check for, okay, compiler. Based on the compiler, you can write CGG, GCC command and check for the errors and execute this program. Okay, but remember, to execute this program, first what you have to do? First is you have to execute this command. Okay, AC on, and you have to specify the path, and then you have to, second step is what? You have to execute the program. Okay, so once you execute this program, okay, will do, it will append 5 records to this particular file. So here what you are doing, you are giving the file path, correct? So in this file, what will be there? All the 5 information will be stored. Okay, all these 5 process record information will be stored to the account file. So what will happen? Third is what? So once third is what? Appends. Okay. Appends 5 process records. Okay, 5 process records to the specified file. Okay. So how many 5 process means? 1 parent and 4 child process. Okay. And if you see here, okay, in this program, we are having one exe command, correct? EXCL. So EXCL will create one more process here. Okay, it will be creating a new process is created by the EXCL in the second child. So there is only a single accounting record for the second child. Okay, even though it is creating one sub child, but here for this there will be only one record. Okay, even though it is creating sub child. Okay, so then after that, after executing the program, then what you have to do, you have to off the, okay, you have to again type this, okay, account on, and you have to this, when you type again the same command, it will, okay, without any arguments, so it will turn accounting off. So when this account on command will execute, it will terminate it. Okay, and this command will not appear in the accounting file. Okay, so these are the steps you have to followed to get the information about the process. Okay, so we have a program here, okay, with the one parent and four child. Okay, this diagram is having altogether, actually it is having how many? Altogether parent, okay, first child, second child, third and fourth, but the second child is again creating one sub child. Okay, but how many information will be stored? Only five child record, five process records will be there. Okay. So what is the first step? You have to run this account on command and specify the file where you have to store the information. Second one is you have to execute the particular program. Third one is, third what happens? Once you execute the program, all the five information about the process will be stored in the specified file. And last one, you have to off the accounting record, okay, by typing the same command again without any argument. Okay, very simple. The next one is user identification. The next topic is user identification. So any process can find out its real effective user or group ID. So user identification is nothing but getting the information about the IDs. What are the different IDs? Real, effective user ID or group IDs. Okay. Sometimes, however, we want to find out the login name of the user who is running the program. Okay. We might be interested with the login name of the user. So for that, what we can do is we can simply call this function. So this is a function we can use. We could simply write this function. Okay. So this will give you, okay, the name of the login name. Okay, this function will give you the specified login name. Okay. But the problem is, what if a single user has multiple login names, each with the same user ID? Okay. So here if you see properly, we have two functions here. One is get UID. So get UID will get the user ID. Okay, let us assume it is getting the user ID something like 0701. Okay. Then what happens is get PWUID will get the login name for this particular user ID. Okay, let us assume that it will give you the name as login name as root. Okay. But the question is, what if this particular ID, okay, is having more than one login names, multiple login names? So for that, the system normally keeps tracks of the name we log in and we can get it using this get login function. Okay, so it provides a way to fetch the login name. Okay, simply you can run this function. So it will give you all the login name, irrespective of how many login names it is having. Okay, all those login names will be provided. Okay, so this will return the pointer to the string giving the login names if everything is okay, or it will give you the null value on error. So this is one function that is used for getting the login name. Okay. So the next topic is process times. So previously we discussed that we described 3 times. So there are 3 types of times, process times. Okay. That is measured using wall clock time. The time can be, okay, we described 3 times. There are 3 types of process times. Okay. And what are the measures? So one based on our clock time, that is our system time or clock time. One is based on the CPU time. Another one is based on the user CPU time. Another one is based on the system CPU time. So there are 3 measures, okay, units. A process can call the time function, okay, to obtain these values for itself and any terminated child. So you can get the process time by using this time function. Okay. And here inside the time function, we are passing a structure as a parameter. Okay. So that structure is defined. This function fills in the TMS, that is structure pointed by a buffer. Okay. So this here we are creating a pointer of the structure named TMS. That is a pointer name is buffer. So that pointer will be pointing to this structure. Okay. And if you see the structure, so structure will give you user CPU time, system CPU time, okay, system CPU time for the child, okay, and user CPU time for the child. Okay. So all this information will be given. So this time function will give you the all clock time in clock ticks if everything is okay. Okay, so what is the measure used here? Measure is, it is based on our wall clock time. Okay, wall clock time. Okay, and time will be given for the process if everything is okay, or it will return you -1 on error. Okay. So this completes your one chapter from fourth module. Okay. So moving on to the next chapter. So here in the first chapter, what and all we have discussed. So first chapter we have discussed changing user IDs. Okay. What is an interpreter file? What is a system function? And today we discussed about uh, process accounting. Okay. Then we discussed about user identification, finding the login names, and the last topic is process time. Okay. So these topics we discussed under that first chapter. Then again you have two more chapters under this module. So moving on to the second chapter. So second chapter is about IPC. IPC stands for Interprocess Communication. Okay. So here we'll be discussing about what are the different ways process can communicate. Okay. What are the different functions we have? What are the different modes or methods we have for interprocess communication? Okay. So that is your chapter 4. Okay. The chapter 4 from Richard Stew textbook. So first is we are studying about a brief introduction about interprocess communication. So here, interprocess communication allows one application to control another application, and for several applications to share the same data without interfering with one another. Okay, so here IPC will allow one application to control another application, as well as it will allow sharing of the same data uh, by several applications. IPC is very important when we are dealing with a multi-processing system. So you might have heard about different types of processing systems, single process system, distributed, multi-process systems and all. So here IPC is very important for dealing with the multi-process systems. Okay, multi-process system means a process that is, a system with a multiple process. Okay, for performing the task. But it is not generally supported for a single process operating system. Okay, so IPC is used only for multi-processing systems. Now here there are different types of IPC methods. Okay, so Unix has different IPC types like This types depends on what type of what version of operating system we are using. So some version supports some types, and other one will support some other type. Okay. So here we have different IPC types like pipes. Okay, or it also called as half duplex pipes. Then FIFO. So FIFO is a IPC type, which is also called as named pipes. And then we have stream pipes, which we call it as full duplex pipes. Okay. Then we have named streamed pipes, or we call it as named full duplex pipes. Okay. And few other like message queues, shared memories, semaphores, sockets, streams. Okay. So we are going to study each of this in this chapter. Okay. The first 7 forms of IPC are usually restricted to IPC between process on the same host. Same host, we can use this first 7. What are the first? 1, 2, 3, 4, 5, 6, and 7. So these are only for the communication between the process on the same host. Okay. And the last 2, that is socket and streams, okay, are the only 2 that are generally supported for inter-process communication between the process on different hosts. Okay, so this is for different host communication between the process, and these are all for same host. Okay. So let's start discussing about the concept of pipes. So pipes are the oldest form of Unix inter-process communication. Okay, and they are provided by all versions of Unix systems. Okay, and pipes have 2 important limitations. Okay, first thing is they are half duplex. So what do you mean by half duplex? So you might have studied in networks half duplex, full duplex, and all. Okay, so pipes are half duplex. That means the data flows only in one direction. So at the time, the data can flow only in one direction. Not full duplex. It is half duplex. Pipes are half duplex. Okay, so one process here, 2 process if they want to communicate. First, this has to send the data. Okay, so then the next one can send the data. It is half duplex. Next limitation is this can only be used between the processes that have the same common ancestors. That means these 2 processes should have common ancestor. So only if they have common ancestors, only then, okay, then only then they can communicate, they can transfer any data. Okay. Normally, a pipe is created by a process. Okay. Who is going to create a pipe? It is created by a process. That process calls a fork function, and the pipe is used between the parent and. Okay. So who will create a process? A pipe. Pipe is created by a process which calls this fork system call. Okay. Then after the process causes fork system call, a pipe will be created between the parent and the child. Okay. So this is a prototype for creating the pipe. So pipe is created by calling this pipe function. Okay. So here this is the prototype pipe function. So it returns 0 if everything is okay, and it returns -1 on error. Now here, if you see here, we have one parameter. So actually parameter is in the type of array, an integer array with the two values. Okay, so this stands for file descriptor. Okay, so there are two file descriptors. Okay, two file descriptors are turned through a fields arguments, that is one is, there are two file descriptors. One is file des 0. Okay, another one is file descriptor 1. So there are two file descriptors, okay, for the pipe. So file descriptor 0 is open for reading. So this descriptor is what? Descriptor is something like a pointer. Okay. So this is file descriptor 0 is used for reading. Okay. And file descriptor 1 is open for writing. So this is used for writing. So don't get confused. First descriptor is used for reading and second one is used for writing. Okay. Then output of file descriptor 1 is the input for file descriptor 0. So here what? Output. So after writing, okay, so this will be given as the input for the file descriptor. So you can see in this diagram, okay, so we have two file descriptor. Concentrate on the first diagram. So this is for file descriptor 0 and this is for file descriptor 1. Output of this file is given as an input for the file descriptor 0. Okay. And this diagram will show you, okay, this is an elaborated diagram. Okay, so you can see here there is a pipe. Actually there is a pipe. Okay, so that pipe or whatever the output we are giving will be in the pipe, and through the pipe that output will be given to the file descriptor, will read that output. It's like a pipe. Okay, you pass the data here. Usually what happens, you pass the water here, it will come out of this. Same way you pass the data. Okay, this is for writing and this is for reading. Okay, you are writing through the file descriptor 1, through the pipe. Okay, file descriptor 0 will read the data. Just ABC you will write, it passes through here, and ABC file descriptor 0 will read that. Okay, so here this diagram, okay, there are two ways to picture a pipe. Okay, there are two ways here. So the left half of the left picture, okay, it shows two ends of the pipe. Okay, two ends of the pipe connected in a single process. Okay, so there is a single process where we are connecting two ends of the pipe. Okay, the right diagram, what's the right hand side diagram? Okay, so it will show a little bit elaborated diagram. Okay, where the data in the pipe flows through the kernel. Okay, actually data will pass through the pipe, but in turn the pipe is there where in the kernel. Okay, so this is a simple diagram, okay, showing the concept of half duplex pipe. And you can see here there is only one way of passing the data. Okay, from here to here, and it is through a single process we are showing this. A pipe is a single process is next to useless. Okay. Suppose in this diagram you can see here you are using a pipe. Okay, but here, how many processes here we are using? Only one process. Same process is writing the data, and the same process is reading the data. Okay, so actually this concept of passing the data uh, through a single process is a useless concept. Okay, so normally a process that calls pipe then calls fork creates inter-process communication channel from the parent to the child or vice versa. So here there is a parent this fork function system call, so that will create a child, and what happens, there is a communication, inter-process communication will start between the parent and the child. A pipe will be created between the child and the parent. Now either the child can pass the data to the parent, or parent can pass the child data to the child. Okay. Here you can see so this parent process is having two descriptors, one for reading, another for writing. Similarly, the child process is having two descriptors, one for reading, another for writing. Okay. Now they communicates, the parent and the child can now communicate using the pipe. Okay. We can see here, let us assume that the child wants to send some data to the parent. What happens? Child writes the data. Okay. So then parent will read the data. Okay. Similarly, now assume that the parent want to write the data and the child want to read the data. Okay. So in that case, what happens? So parent will write the data. Okay. Parent will write the data, and using this file descriptor 0, the child will start reading the data. Okay. So file descriptor 1 is used for writing, and file descriptor 0 in both the side, both the process is used for reading. Okay. So here it is for writing. Okay. This end we are using for writing. Okay. And this end we are using it for reading. So like this, two process, parent and child, can communicate and transfer the data. Now, suppose if we are having a pipe from parent to the child, okay, a pipe from parent to the child, and the parent now will close the read end of the pipe. You can see here we don't have any. Okay, suppose the parent want to write any data to the child. The parent want to write the data to the child. So here you can see here we are not having file descriptor 0, because parent want to write the data to the child. So this end, that is FD0, that is meant for reading, is closed. Okay. So this descriptor is closed. Okay. So parent closes the read of the file descriptor, that is FD0, and the child will close the which end? The child will close now the right end of the file descriptor 1. So this both are closed. Okay. Since parent want to write the data to the child, parent will close the read end and the child will close the write end. Okay. Now what happens? Parent, this is for writing and this is for reading. You know that, correct? So parent will start what? It will start writing the data and the child will read the data. Okay. So how the parent is transferring the data to the child. So when the parent is transferring the data to the child, two ends are closed. That is, at the parent end, read is closed, and at the child end, write is closed. Okay. So when one end of the pipe is closed, the following two rules apply. Okay. So if we read from a pipe whose right end has been closed, okay, if you are reading from a pipe whose right end has been closed, read returns 0, indicating a end of the file after all the data has been read. Okay. And similarly, if you are trying to write to the pipe whose read end has been closed, okay, signal, there is a particular signal that is called as sig pipe is generated. Okay, assume that you are trying to, okay. So what this rule is telling is, okay, actually your process is trying to read a pipe. Here what the child is doing, child is trying to read from the pipe. Okay, but if this is closed, okay, this end is closed, right end is closed, there is no data is coming to the pipe. Okay, so right end is still closed. Then what happens? Read returns 0. Okay, because there is no right end, no data is available in the pipe. Okay, in that case, it will return 0, indicating that end of the file after all the read has been, all the data has been read. Okay, there is no data. Then suppose if we write to the pipe whose read end, if we write to the pipe whose read end has been closed. Okay, if we are trying to write, but this is closed. Okay, this end is closed. Okay, read end is closed. There is no process ready to read the data. Okay, somebody is writing the data to the pipe. Okay, data is available here in the pipe, but nobody is there to read the pipe, read the data. Okay, now what happens in that case? A particular signal is being generated. That is signal is called as sig pipe is generated. Okay, and once this signal is generated, what you can do, either you can make a signal to the particular process telling that data is ready, you can start reading the file data, or it will return 1 with the error. Okay. So what we are trying to tell here is, okay, when the data is available here in the data, in the pipe, okay, some process should be ready to take the data. Okay, and one more case is you are trying to read the data when the pipe is empty. So that is also a wrong, correct, right? When the data, water is not there, and if you are trying to collect the water, what is the point? So here also you have to think of these two rules. Okay. So we have a program here. So this program sends data from parent to the child through a pipe. Okay. So what happens? We know that parent can create a parent can create a pipe using which function? Using fork system call. This one function is enough to create the pipe between the parent and the child, correct? So here what we are doing, here we are creating, a parent is creating, fork function is used. Okay, what this fork function will do, it will create, okay, between the parent and the child a pipe will be created. Okay, okay, there are two descriptors. Okay, so this is for write and this is for read, correct? So now what we are doing, using the file descriptor 1, where is file descriptor 1? That is in the parent. Okay, using that file descriptor, you are writing the data. Okay, you are writing the data. What is the data? I just write simple hello world of length 12. Okay, you are writing this data. Then what happens? Okay, you are closing this. Okay, once you finish writing, okay, you can close this. And then what the description, child is using which descriptor? Yeah, it is using which descriptor? By FD0. So using that FD0, it will start reading all the data. Okay, what is the maximum line? Entire line it will read. Okay, so entire line, that hello world, it will start reading. So what is the descriptor is used? That is FD0. Okay, and finally you can write to the standard out. In the terminal you can display the return data, that is hello world, you can display. Okay, so here this you have to very careful. So when parent is writing, which descriptor it is using? FD1. Okay. When the child is reading, which descriptor it is using? FD0. Okay. So here what data it is writing? It is writing hello world, which is of length 12. And here you are reading that particular line. Okay. A very simple example and very important example. They may ask you explain the concept of pipe. Okay. With a program, explain how you can send the data from the parent to child over a pipe. Okay, so that is all for today. So answer attendance, Naresh.
Present, ma'am.